The last question is, a heat engine with a diatomic gas as the working substance uses the closed cycle shown in figure. How much work does this engine do per cycle, and what is its thermal efficiency? So we need to find the work in per cycle and the thermal efficiency. Let's find the work do per cycle that this engine does. So here four processes like 1 and 2, it's isobaric process, 2 and 3 is isochoric process, isobaric, and also isochoric process. So 1 and 2, let's find 1 and 2, it's isobaric. We know that it's equation P delta V, simple. P is equal to 303 atmospheric 10 to the power 5 times delta V is 3 minus 1 will be 2. So here will be 6 times 10 to the power 5 joule. So 2 and 3, we know that volume will be, if volume is constant, volume is not changing, work equal to 0. The next 3 and 4, they're also P delta V, but here will be minus. Why? Because work done on the gas, work done on the gas, and the volume is decreasing. So here will be P also equal to 10 to the power 5 minus times delta V equal to 2. 1 minus 3, like, so here will be 2 minus 2 times 10 to the power 5 joule. 4 and 1 is also similar, like 2 and 3. Volume is constant, will be 0 joule. So net work or total work equal to this number plus this number. It's 2 10 to the power of 5. So here will be equal to 4 times 10 to the power of 5 joule, our total work. So we found the first question's answer. Let's turn on the second question. The next question is, what is its thermal efficiency? Thermal efficiency means we need to, how we can find? We can find it total work divided by heat, Q heat, heat that gained from the hot reservoir, and times 100%. So we found the first part, total work, and we need to find this part, the next part. So let's find it. Q in each processes, in each part, 1 and 2, 2 and 3, 3 and 4, 4 and 1. So let's find the first 1 and 2. Now 1 and 2, we know that from the first law of thermodynamics, delta U, it's change of the internal energy and plus work. So here will be delta U, as said here, the atomic gas. The atomic gas means here will be 5/2 nR delta T plus work. Work equal to this number right? We don't need calculated work 1 and 2. So 5/2 nr delta t. N is unknown and the delta t is unknown. So let's find it. N equal to, let's find it from this equation. So let's write it here, P1 and V1 and RT1. By this, in this equation, we can find an N number of moles, and the number of moles will be constant to the whole of this cycle, because they're said that uses the closed cycle. Closed cycle means number of moles is not adding some number of not adding and not subtracting. So here we can find it RT1. So here we can't find n in this equation because T1 is not given, but instead of this here T4 is given. So we can convert it for T for the fourth parameters, P4 V4 over RT4, right? So here all these values are given. P1 given, P4 given, V4 given, and T4 is given. P4 here, as we see in this cycle, in this PV diagram, is equal to 1 atmospheric times V4. V4 is also given 1 over R is equal to, we know it, ideal gas constant 831 times T4. T4 is 300 Kelvin. 300. So here, a number of moles equal to 40.1 mole. So we found the number of moles. Number of moles will be constant of the whole this cycle. And the delta T. Delta T, here we need to find T1 and T2. And here also T3, because here will be here this number will be neat for this site, for this part 3, 1. So how we can find it? It's easy. Let's find T1. T1 equal to in this from this equation, ideal gas law, equal to P1 V1 over NR. All these values are given. So P1 equal to 3 atmospheric, volume is 1 over, and number of moles is also given. Also, we found it for 40.1 times 831 ideal gas constant. So here will be 900 Kelvin. T2 is also similar like this equation. Only here will be change P to V2. So let's not waste time. Let's write immediately the number result of calculation. Here will be 2700 Kelvin. T3 also similar. Here will be 900 Kelvin. And T4 is given initially. So we can find by these numbers, by these temperatures, easily the heat in each processes. So let's calculate it. Here will be 2.5 times 40.1 times 831 times delta T is T2 minus T1, right? This change of the temperature. here will be 1800 plus 1 and work 1 and 2 equal to this number, 6 times 10 to the power of 5 joule. So here will be Q1 is equal to Q1 and 2 equal to approximately 210,000 joule, right? So we found the Q 1 and 2 process in this process. So let's turn on the to the second 2 and 3. 2 and 3. 2 and 3 also similar like this, but here will be only change of internal energy because work is equal to 0. So delta U equal to 5 over N R delta T. So all these values are given, right? Here, but will be negative number, T3 minus T2. And moles are given, ideal gas constant given. So let's write result of calculation 2, 3 equal to minus 15 times 10 to the power of 5 joule. So here will be also 2,100,000. I was wrong in this number. So let's write it also in power joule. So here will be minus 15. And let's find the next question, the next process, 3, 4. 3, 4 is similar like 1 and 2, but it will be, there is the compression, right? So it means here will be also negative number. So here will be 5 over 2 NR T plus work 3, 4. So all these values are also given here. T4 minus T3, right? 300 minus 900 will be delta T will be minus 600. So 3, 4 also work. 3, 4 also given. So let's write the result of calculation. Here will be minus 7 times 10 to the power of 5 joule. So, and the last process is T Q 4 and 1. 4 and 1 equal to similar like this, 2 and 3. Delta U equal to 5 over N R delta T. N is given, R is given, delta T also given. Delta T is T4 minus T1. Not T1 minus T4. So let's write the result of calculation. Here will be 5 times 10 to the power of 5 joule. So delta T is T1 minus T4, not T4 minus T1. So we found each of these processes heat energy in each process is 1 and 2, 2, 3, 3, 4, and 4. And we saw that some energy are positive and negative, right? and we need to find the heat, Q heat, heat gained from the hot reservoir. It means heat's energies, positive numbers. Positive numbers will be to this energy. So here only two energies are positive, Q1 and 2 and 4 and 1. So Q heat equal to Q1 2 plus Q4 1. So here 21 plus 5 in parentheses times 10 to the power of 5, right? So here will be 26 times 10 to the power of 5 joule. So we found the two parts of this thermal efficiencies, right? Work total is calculated, and Q heat also calculated. We found. So let's find it easily. Work total equal to 4 times 10 to the power of 5 over 26 times 10 to the power of 5 times 100%. So here will be cancelled these numbers, and 4 divided by 26 approximately 0.15, and we will multiply this to this percent. In percent will be 15%. So we found the answer for the last question. Thank you for your attention.